Laushi, can't hear your voice. I can't hear you.
Oh, sorry. I, okay. Now can you hear me?
Yes, yes.
Okay. Okay. Let's talk about it again. Okay. In previous lessons, we have talked about the pre-order and in-order and post-order of a binary tree. Do you remember? And we have talked about what is a binary tree, and we have talked about some properties of the binary, right? And I ask you guys to write the recursive pre-order program. This is the pre-order function of a binary tree. Do you remember how we traverse a binary tree in pre-order? The first step, we will visit the root of this binary tree. And the second step is we will visit the left subtree of this binary tree. And the third step, we will visit or we will, right? So if you want to write the recursive in-order function of the binary tree, you just need to change the orders of these lines, right? If we write in order, so do you remember the first step we will, which one is in order? If we want to write in order, recursive in order function. So the lines will be like the first two, and then one, and then three, right? So for the post-order recursive, post-order, so it will be two, three, and one, right? Because for the post traversal, the first step is visit the right the left subtree, and the second step we need to traverse the right subtree, and the third step we will visit the root, right? So if you want to write the recursive program of these three traversal, it's very easy, and they are just need to change the orders of these three lines, right? So, and we have talked about the procedure of this pre-order function, how it's executed, right? Because this function is a recursive function. So in this function, we will call itself, right? So we call this function is a recursive function, or we can say recursive program. Okay, so this is the post-order traversal, right? You can say difference is the order is different, right? The first step is left subtree and then right subtree, and at last we visit the root. So the question is, since can we write the line recursive program of these three traversal algorithm? Okay, let's take let's for example to say how can we write the this is the in order recursive. Okay, let's say how can we write the line recursive? Let's take in order for example. Do you remember when we write the in order recursive program? Okay, let's go back to say how the recursive in order function works. Okay. If this is the binary tree, there are 4 nodes in this binary tree, and this is the recursive in order function here. So do you remember in order? The first thing is we will in order the left subtree. So in this example, we call this function with t. So at the beginning, t is the root, points to a. This is the root of this binary tree. So if we want to in order this binary tree, so the first thing we need to in order the left subtree of a. So let's execute this line. So core in order T L child. So we will call TL. That means T will be points to B, right? So, and if we want to in order this binary tree, we need to in order the left subtree of B. Of course, the left subtree of B is long. So we will do nothing. So we go back to the function which call that left subtree. Then we go back here. Because it's long, so we back, return, we return here. And then the second thing is we will visit the root. So we visit B, printf output B. So it's printf B. And then we will in order the right subtree of B. So we will call I in order T right. So now T is B, so right is D. So now the parameter is D, or we can see the root is D. And then as for the binary tree with root D, the first thing we need to do is to in order the left subtree of D. Of course, the left subtree of D is none, so we will return. So it's none, and then we return here. So this is the first thing. And the second thing we will need to do is to visit root. And now the root is D, so we printf D. And then we will in order the right subtree of D, right? Of course, the right subtree of D is none. So we will return. Then when we return, we have finished the in order function of this parameter. Of what we can see, we have finished in order the binary tree with the root D. So we will back. And when we back here, that means we have finished the in order of the tree with root B. Okay, so we will return back here. Okay, now we will visit the root. And now the root is A, so we printf A. And then we will in order the right subtree of A. So that means core in order T right child. So now the T will be C. T will be C. And then since we call the function is IOD, so the first step we will in order the left subtree of C. Of course, it's long, so we'll return. And then we will visit C, printf C, and then we will in order the right subtree of C. Of course, it's long, so we return, and then a return, the return. That means we have finished the in-order traversal of the root of the binary tree with the roots 8. That's the recursive program works, right? Or that's the recursive program execute, the process of executing. And now the question is, how can we write the long recursive? Of course, when we write a recursive program, then the system will supply or provide the stacks for us to call the functions, right? Because in C language or other languages, when you write a recursive program, the system will supply you the stack to execute the program, because we need to store the variables and we will store the parameter of the function, or we need and we need to store the address of return, right? So the system will use stack to implement that. So if we want to write a non-recursive program, we need to create a stack to help us to implement the non-recursive program of this 3 traversal algorithm. So let's say how the non-recursive of in-order program. Okay, so here I write basically it's array here. It's an array here, right? And we use this array to be a stack because, do you remember when we implement every data structure, we will implement in 2 ways, right? Array stack and link stack. Do you remember? Or array queue and link queue, right? So here, I just define a array here. Of course, it's a static array, right? Do you remember when we define or when we implement the stack using array, we just define a dynamic array there, right? And here, for simply, I just write a stack array here. Of course, you can define a dynamic array to as a stack to use. Okay, so here I just define a array here to use it as a stack, and I define an integer here to be the top of this stack. And now the thing is, how can we use this stack to store the nodes, or to what we can say to store the pointer in this binary tree? Okay, let's draw a binary tree here, for example. Okay, if the binary tree is like that, and now if we want to use a stack to implement in order, that means the first node you will visit will be the one which has no left child, right? Why? Can you tell me why? As for this binary tree, this binary link, we just have the root pointer of this binary link, right? So root points to root is a pointer, points to the node A. This is the root. So when we start from A, can we visit A now? Or can we output A? Hello. I'll ask you, someone of you to answer it. Or do you guys know why? Okay. Okay, Hou Huijun, do you know? Can you tell me? It seems you are not there. Okay, the next, 煞机部. So you guys don't know? Okay, I need some response to know how you understand or not. If you have, I don't know. Mustafizer. Am I right about your name pronunciation? Okay. So okay. Okay, let's talk about why. This is a binary tree, right? This is the root. And inverter is for every subtree, every binary subtree. When we want to inverter every subtree, we need to traverse the left subtree and then the root and then right subtree. So since this is the rule of inverter, so as for this binary tree, when we want to get the order of inverter, so the first thing we need to do is to inverter the left subtree of A, right? And as for this subtree with root B, the first thing we need to do is to inverter the left subtree of B, right? Of course, the left subtree of B is long. So that means we can visit the root now because B has no left child. So we can visit B. If B has a left subtree, so we can't visit B because we need to visit all the nodes in the left subtree at the first, right? Do you understand? That's very important in binary tree. Yeah, that's right. Okay. So for this binary tree, when we write the non-recursive program, the first thing we need to find the node which has no left child. That will be the first node we will visit in order traversal. So we will, when we start from A, so we go to left, right? Because we always need to find the node has no left child. And the first step we need to do is to inward the left subtree. So we will go left, right? So we will modify the P. At first, the P start from A. So here you can see every time we will change or we modify P to be PL child. So P start from here. And then we will go left. P will points to B. And when we go left, we need to store A, and or we can say we need to store B. Because after we finish in order the left subtree of B, then we can visit B. So how can we find the B? We need to use a stack. Use a stack to store this node. So here you can say we use a stack to store the address of the nodes which we can visit now, right? At the beginning, P points to A, then we push A, and then go left, P points to B, then we push B. Of course, we didn't push A or push B, we just push the address of A node and B node onto the stack. So here you can say we push A, push B means stack plus top equals to P. P is the pointer, right? Or you can say it's the address of the node, right? So every time we change P will be PL child. And we will do that thing again and again. So we need to write a num here. Num. We write a while num here. Well, P is not none. Of course, now we don't know, we need to write top is bigger or is greater than 0. So we can just say, well, P is not none. We modify P to be PL child, and we store the nodes which we can visit now, right? And this is the if P is not long, so we will go left. And do you remember when we found the node which has no left child, like we have found is B, right? We got it here. So now that means we can visit B. So we can output B. So we want to printf B. So where is B? B is here. B is in the stack, right? Do you remember? Every time when we go left, we store A, store B, and then go left, P is not. So we can write else if P is long, because left time P is long, go left. The left child of B is none, so P will be long. So else P will be B, because we want to visit B. So we pop from stack top plus minus minus. So P will be points to B now, because this is not a real B. This is the address of B, right? This is the address of the node which store B, right? So we pop B from this stack, and then we output P data. And then the third step, the left subtree is none. So we visit the root. And the third step, we
Which is
will
the P
import.
data here? What is the P data here? What is the P data here?
P data.
Yes.
Okay. So this is the logical value of the binary tree, right? Do you remember in the previous lesson we have talked about the link storage structure of binary tree? If we draw the storage structure, we can draw like that. For every node, A, this is the storage structure, right? And there are 3 fields of every node. Do you remember? This is data. And this is the L child pointer. Do you remember? And this is the R child. So this is the logical venue of a binary tree, and this is the storage structure. Or we can say this is the binary link. Okay. So now we will output in the stack. We just stored the address, or we can say we store the pointer here, right? I just write the data to show which address of the node, okay? But in fact, in this stack, we store the address of B node, and we store the address of A node here. So when we pop B, so we pop B, and we visit B, that means we printf output B. And then that means we can in order the right subtree of B, right? Every time when you visit a node, that means you can traverse the right subtree of this node, right? So we will change P to be P R child. That means P now will be P will be P R child. So P will be P will point to D. So when P points to D, so the thing is the same. Thing. When we start from node, that means we will go left, right? Do you remember? So we'll go left. Of course, the left of D is none, right? So we push D, and then we go left. And the left of D is long. So we will pop D from the stack. Then we will visit D. Right? And then we will go right. Of course, the right of D is long too. So else, So we'll pop A. So P will point to A. And now we can visit A, right? And then we change P goes to red. So P point to C, right? And well, so well, noon. The first one is P is not long or top is greater than 0. When top is not empty or when stack is not empty, that means there are nodes we haven't visited, so we can't end the while loop, right? So here we need to write when P is not long or top is greater than 0, then we do the things if else. So now P points to C. So we will, now P is not long, right? And we push C and we go left. Of course, now the left of C is long, So P is long. Then the next loop, P is none. That means we need to pop from the stack. So we pop C. Then every time when we pop from stack, we can visit this node. So we visit C. Okay. Of course, if you draw the binary tree like that, so we have visited all the nodes in this binary tree, but as for this program, we haven't finished. So let's say P goes to red, and the red of C is now 2, and now the stack is empty. That means we have finished the traversal of in order. Okay. Okay, let's see another example. It's more complicated of a binary tree. There are 1, 2, 3, 4, 5, 6, 7 nodes in this binary tree. Let's say how the non-recursive program works on this example. So at the beginning, P start from root, right? This is the root. Okay, so since P is not long, so we store A, because when we got A, we can't visit A now, right? We need to in order the left subtree of A, then we can visit A. So we need to store A here. And then we go left. So P points to B. And now we can visit B, right? Because we don't know is there left child of B or not, right? So we push B and then go left. So we push C. And the next time when we go left, the left child of C now is none. That means we find the node we can visit, right? Or you can say every time when the left child of a node is none, so that means you can visit the node. Why? Because that's in order. Always left child, left subtree, root, and right subtree for every subtree, for every binary subtree, right? So now it's for the binary tree with C root. The left subtree of C is long. That means we can visit C. So where can we get C? We pop from the stack. So we visit C. And then P is here. So P is here. Then we will modify P to be P right child. Because when we visit C, that means the node you have visited root. Now you need to in order the right subtree of the node. So we will change this. We will change P to be P right child. Go right. Of course, the right of C is long 2, right? So when P is long, do you remember we need to do pop from stack? So now we pop PB. So when we pop, that means P equals stack top minus minus. That means we use P to be the address of B node. So we draw like that. So when you pop B from the stack, that means we can visit B. We can visit B here. Okay, every time when we visit a node, we need to goes left, goes right. So P will point to node D. Of course, now P points to D and P is long. So we push D onto stack. And next time when P is not none, we push P and we goes left. Do you remember the function of in order? Because now we can't visit D. So we need to find the node which has no left child. So we will go left. Every time when P is not none, so we go left. Until we find the node which has no left child, right? So go left. P points to E. And every time when P is not long, we push and go left. And then next time P will be long, right? Because the left child of E is none. Okay, so now we need to pop from the stack. So now we need to visit E. And then when we visit a node, we will go right. Do you remember? So P will point to G. And now P point to G. P is not long, so we need to push G. And then go left. So P is long. If P is long, or you can say if P is not long, then we do something else. When P is long, so we will pop from stack and visit this node and then go right. So we visit G and go right. Of course, the right of G is long 2, so we will pop D from stack. So we visit D. So we visit D here. And then every time we visit a node, we will go right. Do you remember? We pop and we visit, and then we go right. So P will point to F, and we push F. And P is not long. If P is not long, then we push F and we will go left. The left of F is long, so we will pop from stack and it's F. So we visit F and go right. The right of F is long 2. So we pop A and visit A, right? So when we visit A, we will go right. The right of A is long and the stack is empty now. So while noon will end, right? Okay, let's take a break for 7 minutes. Okay, the second code. Okay, we have talked about the non-recursive program of inward. So the non-recursive program of pre-word is totally the same as inward non-recursive program. So I will give you guys some time to write the non-recursive of pre-word, okay? You just need to modify some statement of non-recursive inward functions, then you can get the non-recursive program of pre-word, okay? I will give you 10 minutes, okay? Okay. Have you written the non-recursive program of pre-order? The difference of in-order and the pre-order is the timing we visit the root or the timing we visit the node, right? So in order, when we pop from stack, we visit the node. And in pre-order, when we visit the node, we still use the example like that. So when we start from root, this is the root. When we start from A, can we visit A now? In pre-order, can we visit A now? Since it's a pre-order, so every time when we start from root, the first we will visit will be root, and then left, and then right subtree, right? So when we start from A, we can visit A now, right? So in this function here, we can write printf right? Because it's for every subtree. The first node we will note will be the root node because you can say this is the root node, right? So this we will modify the printf we write here. And we visit A, but we still need to store because when we visit the left subtree, we need to return A and then we go right. So we still need to push A. We visit A and push A, and then we go left. Go left, that means P will point to B, and we will visit B and push B and go left. And now P is none. So we pop B and go right. So P will be D. Then we visit D and we push D. And then we go left, right? And the left is none. So we pop D and go right. And the right is none too. So we pop A and we go right. So P will point to C and we visit C and push C. So we go left. Left is none, so we pop C. And go right, the right is none too. So stack is none and P is so stack is empty and P is none. So that means we have finished the pre-order. So the non-recursive program, the difference of them is the location or the order of printf, right? So, this is the non-recursive of inverter and the pre-order. And of course, how can you write the non-recursive of post-order? Post-order will be more complicated than in-order and the pre-order. So I will give you about 10 minutes to think about the non-recursive program of postal order, okay? Okay. So now let's talk about the line recursive program of post order. For the post order, the first step we will visit all the nodes in left subtree and then the roots. And then the right subtree of this binary tree. And then the last will be the root. So that's LRN. So the first thing we need to do is the same as we have done in order, because in order is left subtree, root, and then right subtree. So the first step, they are the same, right? This is post and this is in order. This is post order. So do you remember? Since the first step is to traverse the left subtree of the root, no, of course, the first step, they are the same. Start from A, so we need to push A, and then we go left, and then we push B, and then we go left. So the left of B is long. So that means we have find the first node which has no left child, right? But as for post order, we can visit B now because the second step is right subtree of the root. So we need to push B again. So for the post order, we need to push every node twice onto the stack. So how can we know it's the first time we push or it's the second time we push? So we need to define a flag to mark or to tell us this is the first time or the second time of every node. Okay, so that's why I said it's more complicated than pre-order and in order, because here we need to define a struct, because every time when we want to push A, we need to push a flag to show it's the first time or the second time. So we push A1 and then push B1. And then when we pop B1. So we need to write if else. If flag is, we define this one to be a flag integer. So if flag is 1, that means we can visit B. We need to go right. So we push B again, and now we push B2. That means that's the second time we push B onto stack, okay? So we go right, and then we push D1. This is the first time we push D. So D1, and then go left. Left of D is none, so we'll pop D. So here, for the post order here, we need to define a struct here. Type df Okay, so we push D1 and go left this line. So we pop D1 and push D2. Okay, that is now 2. So we need to pop. Then now the flag is 2. That means we can visit D now because the flag is 2. That means, so we can visit this node. So we visit D. We pop D. Since the flag is 2, so we can visit it. So we visit D. And then when we write the program here, we need to write P is none. So next time we pop B2 because when we visit a node in post order, that means we have visit the binary tree with that node. So that means we have visited old node, one node to pop again. So we pop B2. That means we can visit B. So we pop again, pop A, push A2. And we go right, so we push C1. And go push C2. And go red, the red is none, so when we pop C2 and we visit C, right? That's the non-recursive program of post order. So let's say the function. Same while loop, the same if P is not long. I'm not, sorry, this is pre-word. This is post word. The same while loop, the same P is not none, but the difference from in order and pre-order is here. We need to define the struct. There are two fields in this struct. First one is by tree PTR. It's a pointer, right? Now by tree is a pointer, and another one is the tag integer variable. To show it's the first time or the second time we push the pointer of the node. So P struct to be as node. So when we want to define the array to be a array stack, so we need to define like that as node stack, because in this stack we store the struct. Okay, so here stack plus top equals s. S is a s node in variable. So you can see here we define the s node variable s. SPTR equals to p. S tag equals to 1 because you remember every time when p is done, so we push the node or we push the node as tag. Else, do you remember we need to pop from the stack? And we need to check the stack is 1 or 2. If tag is 1, that means it's the first time. So we can visit node now. We need to modify the tag to be 2. And then push again and go left, right. because we right. So you need to go right at first, and then you can visit the node. So here we will push that node again. So we modify the tag TB2 and push it again and go right. Else, that means if S tag equals to 2, then we can visit the node. So we printf p data. And here, you need to write p equals none. Why? Because when you visit the node, that means we have finished the traverse of this binary tree with the p data, right? With the root of p data. So now you need to get the nodes from the stack, So you need to write p equals to none. Then next loop, you can come here. You can come to this branch because we need to pop from the stack. Okay, let's take a break for 5 minutes. Okay, third code. Okay. We talk about the non-recursive of these three traverser. So pre-order, in-order, and post-order. And the pre-order and the in-order is easier than post-order. But as for the recursive program, they're all easy, right? And let's see how the non-recursive program of post-order is queued on this example. So this is the binary tree, and this is the stack. We start from the root A. So we can't visit A now. So we push A1 to remember this is the flag we defined to show this is the first time or second time when we push this struct. So this is the first time we push, so it's A1. Then we go left. Then we can visit B now. So we push B1. And we go left, so we push C1. And we go left. And now the left child of C is long. So Do you remember? We write while loop if else. So else, if P is not noun, and now P is noun. So else we pop from the stack. So P points to C now. But now, since the flag is C1, is 1, that means we just go to the left subtree and come back. And now we need to go to the right subtree. So we can visit C now, right? We need to push C again. So we will pop C1, and if the flag is 1, so we push C2. To represent, this is the second time we push C, and now we change P goes to red subtree. So of course the red subtree of C is long, right? So when P is long, we need to pop, right? We read the program like that, right? Else, if P is long, so we pop from the stack. So we pop. And now when we pop, it's C2. So that means we have traverse the left subtree and traverse the right subtree. And now we can visit the root. So we visit C. Every time when we visit the node, that means we have finished visit all the nodes in this binary tree with that node to be a root, right? So now what we can do is to pop again from the stack. So pop B1. Since this is 1, so we push B2. And we goes right. Goes right. So we push D1. And P is not, so we go left. So we push E1 and go left. Left of E is now, so we pop E1 and push E2. Okay. I didn't draw the E2 here, so I have drawn the E2 here. Okay, it's E2, and then we go right. So P will point to G, and we push G1, and we go left. The left of G is none, so we will pop G1 and push G2. And that means we need to pop from stack. So the top of the stack is G2. That means we can visit G. So we visit G here, visit G. And we pop again. We pop E2. That means we can visit E because the flag is 2. So we visit E. And then when we visit that E, we need to pop again. So pop D1, and we can visit D. So we push D2. And we go red. Every time when we push again, we will go to red, right? So P will point to F, then we push F1. And we go left, go left. So left of F is none. So we pop F1, and then since the flag is 1, so we push F2. And we go red. Of course, the red of F is none. So we pop F2. Since the flag is 2, so we can visit F. And when we visit F, we will pop again. So we'll pop D2. We can visit D. Every time we visit a node, we will go right. So, sorry. That's post. Every time when we visit a node, that means we have nodes in this binary tree. So we need to pop again. So we pop B2. We can visit. And then we pop again A1. So we push A2. And we go right. Every time when we push again, we go right, right? So it's none. So it means we need to pop from stack. So it's A2. We can visit A. And now P is long. The stack is empty. That means we have finished the traversal of this binary tree in post order. Okay. So do you understand? So you need to after class you need to write the recursive and non-recursive program of these three traversal. Okay. So let's analyze the time complexity of these two traversal. Okay. From the three traversal algorithms, we can know that if the print statement is deleted, the three recursive algorithms are exactly the same. Or we can say the access paths of these three traversal algorithms are the same, but the timing of visiting nodes is different. That's what we have talked about when we talk about recursive program. Do you remember? We start from the root A, and if we traverse this binary tree in pre-order, so the first time when we met A, we will visit it, right? And we will go left. We'll go left. And we will visit B, and go left, we'll visit D. And go left, it's long, so we'll go back. Go back, we will go to the right. Okay, if we in order, when the first time we meet A, we can visit A. We go left and left and left. And if the left of D is none, so we can visit D and we go right. So about the timing, we can say the first time we meet the node, we can visit. This is pre-order. The second time we meet at the node we visit, that means that is in order. And if we traverse this binary tree in post order, the first time we got A, we start from A, we back D. We can visit. We need to go to right. And the second time when we back, we can visit D. So that's the post order. So, but if we count the time we meet that node, this is the first time, and this is the second time. This is the third time for the post order. Okay. So time efficiency and the space efficiency of binary tree traversal. Time complexity will be big O of n. Why? Because we visit each node one time. And space complexity will be big O of n. Why? You will say we haven't defined any integer or any variable for in this program, but the system, when you write the recursive program, the system will supply you the stack if you write non-recursive program, you need to define a stack by yourself. So big O of n is the maximum space of stack. Maximum space, in which case, if the binary tree is the screwed binary tree. So there are n nodes in this binary tree, and you need to supply a stack with n space, right? Because like this is A, B, C, D. So you need to have a supply a stack with 4 space A, and push B, and push C, and push D. And then the left of D is none, so you can pop D. So it's big O of n. And time complexity, since we write the recursive program or non-recursive program, do you remember? In this, let's, for example, when we write non-recursive program, we write while loop to implement the traversal. So there is a statement like printf p data, and we need to visit this node one time. So if there are n nodes in this binary tree, so the time complexity will be big O of n. And since we have talked about this traversal methods, so now let's use this traversal method to resolve some problems. There are 2 questions here, or there are 2 problems here. The first one is count number of leaf node, and the second one is get the depth of binary tree. And I will give you some suggestion. Like the first one, you can use pre-order. Of course, you can use in-order or post-order to do that. And the second one, you can use post-order to resolve this problem. Okay, I will give you 5 minutes to think about how to resolve these problems. Okay, then we will talk about it. Okay. Let's say the first problem, count the number of leaf load. Do you remember what is leaf load? Leaf load means the node has no left child or right child, right? So we call the node to be a leaf load. Just like we call in the real world, the leaf, right? So since we have write the program of a pre-word, in-word, and post-word, and do you remember in these traversal methods, we will write printf p data, right? So every time when you visit the node, you can modify lines to be check the node is leaf or not, right? So these problems, we can use any traversal algorithm to resolve it, right? So as we have talked about here, we use a pre-worder to implement or to resolve this problem. Do you remember this place? In pre-worder, we just write printf p data, and now we can write if to check this node is leaf or not. If t child is not long, and tr child is long, sorry, if tl child is none and tr child is none, this operation means if TL child is none. So we use this option to get the operator value. So it's true. So this will be true. So that means TL child is none and TR child is none. So we count +1. We count it. So is that easy, right? And the second problem is to get the depth of binary tree. This problem, we can use post-worder to resolve it. Do you remember what's the depth of a binary tree? The depth. If we draw a binary tree like that, that means the depth of this binary tree is 1, 2, 3, right? So if we want to get the depth of this binary tree, you can think if the binary tree is an empty tree. In definition, do you remember an empty tree is a binary tree, right? So the depth is 0, right? So we write post-worder is if we can get the depth of the left subtree and the right subtree. So you can say the left subtree, the depth is 2, right? And the depth of right subtree is 1, right? And we choose the maximum or we choose the greater one of left subtree and right subtree, and then we +1. So we got the depth of this binary tree. So these problems, we can write the recursive to implement that, right? Because this program is a recursive program. If we want to get the depth of the binary tree, the first thing is we can get the depth of the left subtree, and the second is we got the depth of the right subtree, and we choose the great one, 2 plus 1, as the depth of the binary tree, right? It just like we have done or we have written in post order, because in post order we traverse the left subtree, and then we traverse the right subtree, and at last we visit the node. So in these problems, we got the depth of the left subtree and got the depth of the right subtree, and at last we choose the maximum or the great one of them and then plus 1. So we can write the program like that. This is the depth function. This is the depth function. And this is the depth of left subtree, and this is the depth of right subtree. And we write if to choose the big one of them, and we got the big one to plus 1 to get the depth of the binary tree. Else, we write this if else. Of course, when we write recursive program, we need to write this if to give the end case, right? The end case, what we have talked about, you can think an empty binary tree. The depth of this empty binary tree is 0. So here, if T is not means this binary tree is an empty binary tree, right? So we can return 0. So this is a typical recursive problem, right? Like A, B, C, D. So you want to know the depth of this binary tree. You need to know the depth of this, and you want to know the depth of this binary tree. You need to know the depth of the left subtree of B. Of course, the left subtree of B is empty, so it's 0, right? And the second step is you to get the depth of the right subtree of B. So the depth of D, of course, the left of D is 0, and the right of D is 0 too. So we can know the depth of D is 1 because they are the same. So 0 plus 1 is 1, right? And we check 0 and 1. So 1 is the big one. So 1 plus 1 is 2, right? And then we got the depth of C is 1. So we choose the big one is 2. And 2 plus 1 is 3. So we got this depth of this binary tree is 3, right? This problem is a recursive problem, or you can say you can use the recursive algorithm to resolve this problem, right? Okay. And I will say another example or another question to use the traversal method to resolve, okay? The question is how to create a binary tree. Since we talk about the traverse method, we assume that we have create a binary tree. So now here is the question, how to create a binary tree. We can use a pre-order to do that. Let's see how can we do that. If we want to create a binary tree, we can say we can create the tree if the tree is an empty tree, so it's a binary tree, right? And if the tree only has a root node, so we can use malloc to ask for a node or ask a memory block for this node, right? And this is A, and the left child is none and the right child is none, right? But if the tree is not empty, or the tree is not just have only one root node, if the tree is like that, or if the tree, this is the logical value of the binary tree. If the binary tree is like that, so how can we create it? When we talk about create, that means how can you store or create or ask for the memory block of this logical value A, B, C, D, E, F, G, right? That means create. This is the logical value you just draw on the slide. But in memory, how can you store this binary tree, right? Or how can you create a binary link? A binary link. This binary link, do you remember? In the memory, it's A and the left child, right child. This is pointer, right? This is B. Do you remember? So the purpose of this problem or the purpose of this question is how can you create this binary link of this binary tree? And C is a node, and this is C. This is the left child and the right child. Okay. So if the node question is like that, why we write question mark here? This is, we use the question mark to represent the left child or the right child of this node is none. It's none. Okay. So you can say this node sequence is the pre-order sequence of this binary tree, right? Let's see together. This is A, B, D, and question mark, and E, question mark, and G, and question mark, and C, and F, and question mark. F, and the question mark, and question mark. So this is the pre-order sequence of this binary tree. Why we need to add this question mark? Because we need to know D. The left child or the right child of D is none or not. So when we want to use this pre-order sequence to create the binary link like that, we can write the recursive program just like we have write the recursive program of pre-order. Like when we read A, this is the pre-order sequence, right? When we read A, that means we can create a new node for A. And the second thing is we need to create the left subtree of A, and then we need to create the right subtree of A. So here you can say it's a, basically it's a pre-order recursive program. Just we change the function name because here we didn't printf. We just ask for the memory block of this node. So the same reason of the parameter why we define this parameter to be a pointer which points to a pointer, right? Because by tree is a pointer. So root is a pointer, points to this pointer, okay? Because in this function, pre-create by tree, we will modify this parameter and we want to this change will return to the function which call pre-create by tree. So here we define the parameter to be a pointer, points to pointer, okay? So the first thing we will do when we read A, so we will create, or you can say ask for the memory for A. So we can, and we use data to store A. So here, root data equals to ch. And then the second step, do you remember in pre-order, we will go to the left subtree, right? So here, we will create the left subtree, So how we reference the left subtree? Because root is a pointer, points to the root, which points to the node, okay? So here you can say we use star root L chart and we use this and to get the address of this root, of this pointer, So that means we need to create the left subtree of A, and then we need to create the right subtree of A. Okay, let's take a break for 5 minutes. Okay, the last code. Okay. This is the program we use the algorithm of pre-order to implement how to create a binary tree like that. So if you want to create a link binary tree, if you can give the node of pre-order sequence, of course, this is there are some difference about this sequence from pre-order sequence because in this sequence you need to give if the left child or right child of a node is none, you need to use a question mark to represent that. Because when you want to create this binary tree, if you want to create the binary tree with root D, so now you can create, you ask for memory for D, and then you call the function itself, create binary tree. So you will read the next chart is question mark, So that means it's an empty tree. So the left subtree, it will be none. The right subtree will be none. So that's the difference about pre-order sequence and this node sequence. If you want to use pre-order algorithm, recursive algorithm to resolve or to create a binary tree, you need to give the sequence like that. Or you can say that's the pre-order sequence of the binary tree like that. This is the logical value of this binary tree. Okay, In this lesson, we talk about the non-recursive algorithm of these three traversal methods. And we talk about some problems which we use these three traversal method to resolve them. Okay, so the lifetime of this class, you need to write the recursive and the non-recursive program of pre-order, in-order, and post-order. Okay.
Okay, that's it for today. Goodbye, everyone.